of all, clarify that I don't think in this lecture it is necessary to explain the importance, the medical importance and significance of the blood group. It cannot be overemphasized. So instead of giving long speeches to explain how important it is, I think I jump immediately into the discussion of that topic. And let's first see the clarification of the most important terms. We are talking about blood groups, and blood groups are looking into so-called group systems. Within blood group, we are going to discuss the agglutinogens and agglutinins of the particular blood groups. But before we do that, with the two most important blood types, or blood groups, the ABO and the H blood groups, I would like to talk a few words about the so-called group systems. The group systems for the first blood group was discovered in 1923 by Landsteiner, who compared who mixed the different bloods and observed that certain combination of bloods result in precipitation or clumping the blood, the red blood cells. And of course, there were very long history for medical failures, starting with the medieval ages when early attempts were made to transfuse blood from one person to the other. And sometimes the blood transfusion was successful, at least the patient survived the blood transfusion. But observation, certain type, certain combination of blood, certain transfusion resulted in lethal outcomes, which always cut back the attempts to make the transfusion, because the number of the failures, the number of the later consequences was too high. So the whole story started in 1973 when Landsteiner started to study systematically. So he started to mix them, and he started to describe which type of bloods give pumping or coagulation in other type of blood, and he, with this systematic and very descriptive way, finally he concluded there are certain blood groups, blood types amongst the human, and he named the first blood group, the ABO type, just simply using the first letters of the ABC to mark the different groups of people whose blood, mixing them together, did not give fatal coagulation. So the whole story started here. Since then, we have more than 30 blood groups, which are all independent. And very important, ABO blood group has nothing to do with the RH blood group. They are completely independent, but the two most important blood groups, the ABO and the RH, what we are going to discuss here, all the others carries, of course, high clinical importance, but only clinical hematologists will discuss that in surgical practice or just the general practice. There is two main blood type or earliest discovered blood type will be. So let's start with the general properties. In each case, when we have a blood group, we always have two components in the blood. We have the agglutinogen. Agglutinogen, which is analog with the antigen as a term, practical engine, but hematologists use this term, agglutinogen, referring to the agglutination. Agglutination is the clumping, the precipitation of the blood. So we have the agglutinogen, which always located onto the surface of the red blood cells, and we have the agglutinins. Agglutinins, which are proteins, immunoproteins, which are dissolved in the blood plasma. And when the appropriate agglutinogens and agglutinins are brought together, they always results in precipitation. As a general rule, we can apply the following. Usually, every blood type, blood groups, has different sets, different lists of agglutinogens and also agglutinins. But as a general rule, whatever agglutinogen we have in our red blood cells, we never have the agglutinins against this agglutinogen in our blood plasma. Evidently, if we would have it, that would be fatal consequences. So the person who has a certain type of agglutinogen always have agglutinins against different type of agglutinins in his or her blood plasma. So this is the general rule. Let's start in the area. So this is the blood type, the classification. Agglutination is the reaction. Agglutinin is the substance, what causes the agglutination. Agglutinogen is the antigen. And transfusion is the process when we add the donor's blood to the recipient in whatever amount. Doesn't matter, small or large amount, transfusion doesn't differ to the amount. Let's start with the ABO system. ABO system basically has two major ABO system has two major agglutinogens, A and B, which agglutinogens are determined by several genes in the body. Basically, the concept is that we have a core agglutinogen on the surface of the red blood cells. This is what is determined by the so-called H gene. This gene is common in everybody. This is present in everybody in respect to the particular blood type. And this agglutinogen is further modified by other genes which will attach one other carbohydrate group to this whole agglutinin, resulting the A or B agglutinogen, which sits, as I mentioned, on the surface of the red blood cells. When the molecule core structure is not modified, this is what we call O type, the absence of the modification. So that will result three basic agglutinogens, the O, which has no antigenic properties, carries no antigen activity, and A and B. The whole system. So when we have the type A agglutinogen on the surface, as I mentioned, we have always agglutinins against the B. Then we have B agglutinogens, we have agglutinins against the type A. In cases when red blood cells carries both A and B agglutinogens, no agglutinins are found in the plasma. When somebody has type blood type O, this is absence of the modification, having only the core molecule. This small core structure does not stimulate the immune system and does not produce any agglutinins. So in these persons, in these subjects, when we have only the H agglutinogen on the surface, we have in the plasma both anti-A and anti-B agglutinins, and when we have both the A and B, we have no agglutinins in the blood. So these are the combinations. Again, having A on the red blood cells, we have anti-B in the plasma. Having B on the red blood cells, we have anti-A on the plasma. Having both of them on the red blood cells, we have no agglutinins. And having neither A nor B, so where we have only H, we have both anti-A and anti-B. This is basically the so-called ABO system. So these are the possible mixtures of blood. When O is mixed with O, no agglutination, but O with A and B, since it carries both anti-A and anti-B agglutinins, results agglutination. These are the possible combinations. It is not the but because of this coagulation, both the kidney and other organs will malfunction. And if the amount of the blood, the so-called incompatible blood, what you transfuse, exceeds the 100 milliliters, the consequences can be lethal. So you don't have to transfuse a whole liter of blood or 2 liters, a few hundred milliliters already lethal. So this is the ABO system. This is what we determine. We so this ABO system is present at the moment of the delivery. All newborn carries both the agglutinogens and agglutinins, which are determined with a codominant inheritance from the parents, and actually it is used in the forensic medicine to determine what is the birth father of a child. Other blood type system is the RH system. This was the second discovered. The RH, the abbreviation, the acronym comes from the Rhesus macaquus, the name, the Latin name of a monkey. You know this rhesus monkey is a popular experimental animal. What the researchers observed when they isolated the red blood cell of this, this monkey, and they transfused only the red blood cells of this monkey to a guinea pig or rabbit, to an experimental animal. So the experimental animal, either the rabbit or the guinea pig, produced antibodies against the red blood cells, what was transfused, when they mixed the blood of the guinea pig with human blood. In some cases, 75% of the cases, they formed precipitation. What does that mean? Probably Rhesus macaquus, the monkey, has similar antigens on the surface of the red blood cells than the humans. So this is where the name comes from. Okay? Those persons who are Rh positive carries the same antigen of agglutinogen, what commonly found on the surface of this monkey. The inheritance is somewhat more complicated than in case of the ABO system, because this blood type is determined by basically by two genes, the so-called D and the CE genes, and why the B genes has only two. So on this locus we have or we don't have the gene present. In the second locus, we might have several alleles present, C or E alleles. There are dominant and recessive alleles, and the combination of this and this gene is going to give us the genotype of the subject. Basically, what we want to remember is that Rh positivity or negativity is determined primarily by the presence or absence of the D agglutinogens. When we have D agglutinogens, the person will be Rh positive. In the absence of the D agglutinogens, the situation is a little bit more complicated. At first hint, in the absence of the B agglutinogens, we regard the subject to Rh negative. However, if we take a short look to the structure of the D protein and the general structure of the CE proteins, we can see the great similarity. Actually, there are only a few amino acid differences. Probably the two gene was generated by gene duplication during the evolution, and one gene, the gene D, remained the same, while there was some mutation in the other gene, resulting the C and E possible alleles in both dominant or recessive form. When we have the dominant forms of this protein, that sometimes gives D positivity to the blood because of the similarity. But the agglutination reaction is much weaker, so we don't see the strong precipitation of the blood. However, after multiple transfusions, the immune system can be sensitized. So, for example, patients with leukemia who regularly receive bloods, the agglutinins against these agglutinogens can be produced in larger quantities, resulting transfusion side effects. Therefore, before the transfusion, we always test the agglutination. We don't simply accept the presence or absence of the agglutinogens. We test the mix, the bloods, and in case, doesn't matter what the genotype says, if we see some precipitation, the blood will not be transfused. So as I said, these are rare cases when the C and E, the dominant form of C and E, generates positivity. Basically, as a general rule, we take this. When we have D, this is Rh positive. When we do not have D, this is usual Rh negative, but in some cases, C and E agglutinogens can also produce weak Rh positive reactions. Okay? Another difference compared to the ABO system, while the newborn carries both agglutinogens and agglutinins in his or her blood. In case of the Rh system, Rh negative newborns do not have agglutinins in their plasma. As we say, Rh negative persons, in order to carry anti-B agglutinins, have to be sensitized first. What is the sensitization? Sensitization is transfusion. When I say transfusion, it can be microtransfusion. A few hundreds of red blood cells is enough to awake the immune system, to sensitize the immune system, and once it is ignited, it is going to produce the anti-B agglutinins in large quantities. So if we have here, probably 25%, this is the fraction, of our classmates are Rh negative. Those who have never received blood transfusion or who never got in contact with Rh positive red blood cells do not carry these anti-B agglutinins. In case somebody already met with Rh positive cells, the immune system is already active and the agglutinins are present. For example, a mother, Rh negative mother, delivering Rh positive baby. During the delivery, when the vessels of the placenta opens, the blood can mix. This is enough to activate the mother's immune system. So if an Rh positive, Rh negative mother carries an Rh positive baby, during the first pregnancy, there will be no any complication. During the second pregnancy, if the blood mix, and 99% of the cases, during the natural delivery, the bloods are mixed, the mother already carries these agglutinins, and unfortunately, the agglutinins of the Rh system in size, the molecular weight is very small. It can penetrate the placenta, and during the second pregnancy, the mother's agglutinins are going to attack the baby's red blood cells, resulting in hemolysis. As the number of pregnancies progresses, the immune reaction is stronger. So in the first pregnancy, no complication. In the second pregnancy, we might have some complication. And third, fourth pregnancy might result in a baby. The mother is not able to carry out miscarriage. This incompatibility will result. This incompatibility within the ABO type never results any complication because the agglutinins of the ABO blood types are too large, they don't penetrate the placenta, only RH. Of course, researchers work very hard to prevent this situation, and luckily it is very easy to prevent the complication. In case we have an RH negative mother, and 25% of the females are RH negative, within 24 hours of the delivery, with exogenous, large quantities of exogenous anti-B agglutinins are administered. These agglutinins are going to hunt down the red blood cells of the baby, which enter to the mother's circulation. They are going to cover, mask the agglutinogens, and the mother's immune system will not get contact with the baby's red blood cells, and the complications are prevented. You might ask the question, why don't we test the father blood type before we do, or we don't do this intervention? Frankly, physicians never trust anybody, so when we have a female, an RH negative female, whatever is the blood type of their husband, physicians are going to suggest this preventive step, and most time mothers don't argue with exactly. And this way you can protect the mother for as many deliveries as you want, so complications will never be. Here is the explanation. So the first immune response which develops, so that the RH system produces two antigens or agglutinogens, and one of them, because of the molecular transfusion rules. Ladies and gentlemen, tomorrow at 9 o'clock, Professor Sabo, the clinical hematologist, is going to come and going to explain this. I don't want to spend time with this part, only one principal rule what I want to declare. I know when I was a high school student, in our biology book, we had a table explaining when we have let's say blood type 0% as a donor, this one can be transfused to anybody because all type of red blood cells don't have the agglutinogen globulin. From now, remember as a general rule, there are no general donors, there are no general acceptors. We transfuse blood only with the same blood type. And many times, the blood type, the different blood types, several, especially after multiple transfusions, more than the ABO and RH blood types are tested in order to prevent the complications. Okay, so no general donors, only the same blood type is transfused. With this, I close the blood types, and we start the discussion of the plasma and the enterohepatic circulation of the bile. This is English, right? Blood is more viscous as the water, and the pH of of the blood, pH of the plasma, phrasing it more accurately, is found between 7.35 and 7.45. Ladies and gentlemen, when we, in the future, memorize clinical standards, clinical values, and I promise you are going to memorize all that, we should remember not only the average value, but the physiologic range. And you are going to see some clinical parameters, some physiologic parameters scatters in a surprisingly wide range. And all of these values are physiologic. In case of the pH, the physiologic value range is very narrow. So when we say acidosis, shifting the plasma pH to acidic direction, please don't say on the exam 5, 2, or 1, because I myself, during 15 years of clinical practice, witnessed one time only pH 6.9, following a very severe intoxication, and who so didn't survive. Relatively small changes in the pH have very hard consequences on the body function. So pH range is very hard. Okay? Color, of course, depending whether it is arteries or vein blood can be different. Components of the blood. Referring again to your high school studies, bloods are composed of so-called formed elements. Majority of these are red blood cells and white blood cells in smaller quantities, and the plasma. In the remaining part of the lecture, I'm going to focus on the plasma. Red blood cells were explained yesterday, if I'm correct, or Monday afternoon, by Professor Beck. So, plasma, which is roughly half, or somewhat more than half, of the volume of the blood, and 93% blood, water, and 7% viscous solids. What is the function? Blood is a very complex organ. During our physiologic study, during these 2 semesters, we are going to reach back always to the blood, and every organ which functions in our body are in contact with the blood, and its function is basically regulated, determined, or supported by the blood. So a lot of hormones, a lot of nutrients are present in the blood. Every time in the different chapters we are going to discover. Basically, however, blood transports nutrients, oxygen and carbon dioxide. The transportation function of the red blood cells will be discussed with regard to the respiration function. Waste products, metabolic and other waste, a lot of hormones, and as you will see, blood plays key role in the thermoregulation of the body, because in every minute our blood makes a complete circle from heart to heart, which means it interconnects the core part of the body with the body surface. So when in the arterial system it reaches the surface, it is going to transport heat. Usually on the skin, in the body surface, it cools down, so the returning blood temperature is lower, resulting heat exchange. Practically, all the heat what the body generates during our daily metabolic activity is transported by the blood to the body surface, from where it is radiated to the environment. So we cannot forget, we are going to see at the regulation of the circulation how important is the blood in regulation the core temperature. And of course, it has a very important immune function and wall clotting, as we will see tomorrow when the hemostasis will be discussed. Composition of the plasma. As I said, 93% of water and a large amount of proteins. 6-7% of the total mass is protein. Usually we give the 70 grams per liter as protein content for the blood, and most of the protein, about 60%, is albumins, which have key role in determining the oncotic pressure. In a few minutes I'm going to explain this term, oncotic pressure of the plasma. So we have globulins, most immune functions. We have the fibrinogen, which plays a key role in the blood clotting, relatively large quantities. But the fibrinogen is precipitated, so following the blood clotting, we don't call the fluid, the extracellular fluid of the blood plasma anymore. We call it serum. Serum definition is basically fibrinogen-free plasma when the clotting components are already removed or eliminated. And a lot of regulatory complex hormones. We have other solutes, electrolytes, organisms, whatever. If you look at the concentration data, what is the physiological concentration of these components, you will notice, you are going to notice, the most abundant component of the blood plasma is the sodium chloride. Basically, sodium ion and chloride ion. That is the 90% of the osmotic activity of the plasma. Other electrolytes, calcium, magnesium, bicarbonate. Bicarbonate is relatively high, 26 millimoles per liter, but the other electrolytes are less than 10 millimoles per liter, which also add further osmotic activity. The osmotic activity of the arguments, the protein, because of their big molecular weight and low molecular number present in the plasma, the participation or contribution of the osmotic activity to the total osmotic activity of the plasma is relatively small. 2%, 3%. However, capillaries are highly penetrable for the ions, sodium, potassium, and almost impenetrable for the proteins. In the same time, we have this protein concentration in the plasma, but the so-called extravascular or extravasal or extracellular space is practically free of protein. Which means between the extravasal and intravasal space, there are no ion concentration differences. The concentration is the same, but we do have protein concentration differences. So the osmotic concentration difference origins only from proteins between the plasma and the extravascular space. This way, plasma proteins are going to be responsible for the osmotic concentration difference between plasma and extravascular space. Doing this, they determine the direction, the move of the water between the capillaries and the extravascular space. So, while numerically this is a very small value, only 2% of the total osmotic concentration, since these ions do not generate differences and driving force always originates from differences. Here we have big differences. Basically, the movement of the water is determined by the proteins. We are going to see the consequences in our later studies, but there will be a lot. Edema generation and others will be basically determined by this. And in the remaining part of my lecture, I am going to discuss the so-called enterohepatic circulation of the bilirubin, the degradation product of hemoglobin, or molecularly Professor Bennett already explained the structure of the hemoglobin, and also in the biochemical study you are going to spend a lot of time to understand simply this degradation, the heme. Today, because of its extremely high clinical importance, we are going to see what happens to this degradation process. Bilirubin concentration is routinely determined in clinical practice, and we are going to see in both family practice, neonatology, and surgery, the importance is very high. So, basically, at this slide, I simply mention there is an average or expected lifespan of red blood cells. Usually it is given between 90 to 120 days. So after this time, they are going to die, they are going to disassemble are metabolized. Of course, proteins are degraded into amino acids, which will return to the protein synthesis. We are going to focus on the hemoglobin here, so the red blood cells are produced, then the hemoglobin is degraded. Basically, it is split into two major components, the hem and the globin. Globin is out of interest this time, and we are going to follow the fate of the hem. Hem, at the first step, basically further split into the iron and the organ component, which is called biliverdin. This biliverdin is a very complex multi-ring molecules, which will be first the large ring will be open left, and from the biliverdin we produce the bilirubin. In the remaining part, we are going to see what happens to the bilirubin. Bilirubin metabolism is very important clinically. Basically, bilirubin is excreted into the bile and leaves the body via feces, but we will see the whole image will be a little bit more complicated as this. First of all, so this is the catabolism. We generate the bilirubin, and what we have to understand when the bilirubin is produced, gets into the bloodstream, mainly into the plasma. Plasma is going to carry to the liver. Next step of modification in the liver, then it is excreted into the bile, and when it enters to the bile, it is released into the GI tract, and in the GI tract it undergoes further modifications. These modifications are basically oxidizing steps. The bacteria in the colon are going to oxidize, and further products will be generated from the bilirubin. So bilirubin, what reaches from the liver, the GI tract. The first step is urobilinogen, urobilin, stercobilinogen, stercobilin. These are oxidized products of bilirubin at different grade or degree. Basically, in the clinical practice, all these components are called, for technical reason, urobilinogen, UBG. Remembering that behind this name, we understand the whole set of differently oxidized compounds. Okay, so next part of the lecture, when I say UBG, this is how in the clinical practice we call urobilinogen. Under this UBG, I understand several different compounds. Alright, quantitative aspects. Roughly 600 milligrams of bilirubin is formed in our body every day, and only 70 to 80% of this bilirubin originates from the heat of the red blood cells. The remaining part of bilirubin is the so-called early label bilirubin. It comes from other proteins, which also in the mitochondria, for example, we have enzymes which also have this heat product. So altogether, we are going to metabolize roughly 600 milligram bilirubin. This will undergo the sequence what was already discussed. Let's see the physicochemical properties of bilirubin. Bilirubin is almost insoluble in water. It's a lipid-soluble compound, and if we look at the structure, we will understand a lot of double bonds, and it's a big organic molecule, relatively small number of hydroxyl groups of charges that makes it totally insoluble. Therefore, when it is transported in the plasma, the majority of the bilirubin binds to albumins. There is no specific bilirubin binding albumin. There is no specific carrier. Almost all albumins which are present in the plasma binds bilirubin in smaller or larger extent. So this is a non-specific binding to the proteins. Since this is a relatively strong hydrophobic bond between the bilirubin and the protein, when in a clinical chemical test the bilirubin concentration is different So we want to, this is a color reaction, so-called diazo reaction, where everywhere in the world, clinical bilirubin concentration. This diazo reaction cannot see the bilirubin which is bound to the albumin. To make it visible, to make it detectable, to make it measurable, we have to detach the bilirubin from the albumin, and treating the plasma with high concentration mineral or alcohol is going to detach it and will bring the bilirubin into solution. This is why the two terms, direct and indirect bilirubin, was introduced. Direct bilirubin determining the freely dissolved bilirubin content in the plasma. Indirect bilirubin is the fraction, actually 6-10 times more bilirubin binds to the albumin than the amount that is found in the plasma. This is called indirect bilirubin. This so-called indirect bilirubin also named by a different name. As we will see later, as the catabolism of the bilirubin proceeds in the liver, glucuronide groups are attached to the bilirubins, which makes the bilirubin water soluble. This so-called conjugated, because bilirubin is conjugated with glucuronic acid, actually two glucuronic acid is attached to the bilirubin, making it water soluble. Therefore, the majority of the direct bilirubin is the glucurinated, the conjugated form of bilirubin, and the majority of the bilirubin which binds to the albumin is not conjugated with glucuronic acid. This is the lipid soluble. These are two different terminology, but naming groups of bilirubins which are 99% overlaps. Of course, it just comes from the thermodynamics. We always find some unconjugated bilirubin freely dissolved in the plasma, but the amount of this bilirubin is negligible. The majority is glucurinated. And of course, the majority of the bilirubin bound to albumin to be unconjugated, so I can almost put an equal sign between the unconjugated and indirect, and between the direct and conjugated. However, this is not completely true because a few % difference exists because of the solubility constant. Okay, so these are the two names what we are going to use. Liver constantly uptakes the bilirubin, and the carrier, the albumin, cannot cross the hepatocyte's membrane, so the albumins remain in the circulation. Liver uptakes only the bilirubin, and there comes the so-called glucuronation step, the conjugation step, when the two glucuronic acid is attached, and this transformation makes the bilirubin immediately water soluble. So this is what we call conjugation reaction. Sometimes in different diseases, genetic defects, two different enzymes does the glucuronation, the first and the second one. Sometimes the second enzyme is missing because of mutation or genetic defect. In this case, the excreted bilirubin will be bilirubin monoglucuronate, but under normal circumstances, the bilirubin which is excreted into the bile is bilirubin diglucuronate. So two glucuronic acid is present. Then it is excreted in the bile and flows down on the bile duct and added to the chymus, the content of the GI tract, and here in the GI tract it will play a very important physiologic role. Not simply eliminated from the body, but it is going to act as a dispersion. It is going to disperse the lipids. It supports the digestive processes because the lipid droplets which are formed in the chymus will be broken down to smaller droplets by the bilirubin because its amphoteric nature it is going to form a layer on the surface of the droplets, making them more water soluble, increasing the surface and facilitating the activity of the lipase enzyme to break down the triglycerides in the thymus. So this is not simply a waste product. This carries very important physiological roles. In the absence of the bile, the digestion of the lipids slows down significantly. These are the explanation that I already discussed. So unconjugated, conjugated, catabolic unknown, yes. When it enters into the GI tract, here comes the next important step. Let's go into this. So this is the, let's say, the map. Here is the hemoglobin, bilirubin is produced, bone to albumin, liver takes it up, glucuronation goes to the bile duct. Here, it undergoes the bacterial transformation, and 90% of the excreted bilirubin is going to be reabsorbed. It reabsorbed to the circulation, then from the blood, the liver is going to accumulate it again. This is why we call this process, this false circle here. It is going to make again the bilirubin diglycoside from these reabsorbed compounds. This is why we call this part enterohepatic circulation. Enterohepatic circulation of the bile. Bile is excreted from here. It does its function in the GI tract, then it is reabsorbed. Daily recirculating amount of bile is several grams, 5 to 6 grams. How is it possible if we produce only 600 milligram daily? Because it recirculates several times, take this circle. Ladies and gentlemen, the time is over. I'm going to interrupt at this point, and tomorrow morning we are going to continue. Thank you.